I'm a computer scientist. I've been doing research on high-performance computing and supercomputing for 30 years, I believe, and have some heavy involvement in the blue water systems that is here, and some heavy involvement now that I spend most of my time at Argonne with our big Mira system, which is a competitor to our supercomputer system. So I have my hands in two of the largest supercomputers in the world, which is nice. So let's move, if we can. No, we can't. We can try to use that. Hope it works. So I found a nice animation on the NCSA website explaining why we use supercomputers. So I'm just going to save my voice and have them explain. And there are a few mistakes in that animation, so if you find them, you get an extra pizza slice. Let's go back. Sorry about that.
What is mathematical modeling? When most people think about the work of scientists and engineers, they think of people in white lab coats who do experiments with test tubes, or people who observe stars and planets with powerful telescopes, or people who tinker until they've built a better mousetrap. Experiments and observation are certainly important parts of research, but there is also a third way that scientists and engineers work: mathematical modeling. Math is the language scientists use to describe the world. Consider gravity. You might describe the way gravity works on Earth as what goes up must come down. A scientist might describe Earth's gravity like this, which means that an object falling close to Earth's surface increases its velocity by 9.81 meters per second every second. Multiplying that number by the number of seconds falling will tell you the velocity it gained during that time. That is a mathematical model, a way in which to describe something about the world with math. Of course, scientists and engineers use mathematical models that are much more complex. This is because they are describing and predicting much more complex things like weather, climate, earthquakes, the formation of galaxies, the spread of diseases, the interaction of molecules, the movement of traffic in big cities, and much more. Think about how many variables affect the formation of a tornado: temperature, wind speed, direction, precipitation, and more. And then we have to think about how all those relate to each other and how they change over time. It's so complex and involves so many mathematical calculations that it can't be solved with pencil or paper, or even a single computer. To study something as complex as weather, you need a super fast, super powerful supercomputer. Supercomputers can help solve complex physics, biology, chemistry, economics, psychology, and engineering problems. NCSA's Blue Waters supercomputer can do quadrillions of calculations every second. If you challenge Blue Waters to a math race, in the first second, the supercomputer would finish thousands of trillions of calculations, while even the smartest, fastest human math expert would have only finished one. It would take a person millions of years to do the number of calculations that Blue Waters can do in 1 second.
Okay. Anybody, anything that was annoying on this animation?
Is it thousands of?
No, just an animation that was wrong. The weight falling down was falling down at equal speed rather than equal acceleration. So if you are a physicist or a mathematician, you are annoyed by these mistakes. Anyhow, what animation didn't explain is why do you do modeling rather than experiment or analysis. And the point is that we cannot observe everything. In particular, we cannot observe the future. So if you want to know what will be the weather in 10 days, you can wait 10 days, but there are reasons not to do it, or climate in 50 years. Can be too small, like understanding biomolecular behavior. It can be too far, like astrophysics, understanding what's happening with supernovas, or too hot, understanding how a combustion works, or things which are hard to observe. Too expensive, and that's where supercomputers are used in engineering. You can design an airplane by putting models in a air tunnel, but air tunnels are expensive. wind tunnels, I meant, sorry. Wind tunnels are expensive, so if you can do it via simulation rather than putting a model in a wind tunnel, then you save money and you do it faster, which is also quite very important. DOE, which is now my employer, is very keen on simulation because, strangely enough, it is not allowed anymore to explode atomic bombs, so it needs to simulate them rather than experiment with them. As an example, people do simulation of what will happen if anthrax is dropped in middle of New York. You don't want to experiment, you want to simulate. So I put a few movies of simulations to give you an example, to give you some example. That's an example of basically a simulation of weather over whatever, 10 days. And you can see basically tropical storms. There was one moving. Luckily, it didn't come to the coast. So you get pretty accurate simulations. This simulation, by the way, is, I think, with a resolution of 10 kilometers, and I shall say later what I mean. But basically, every 10 kilometers, you put a point on the globe, and that's so it means that you will see features which are larger, are tens of kilometers. A feature, a cloud which is only 1 kilometer wide, is totally lost in these kind of simulations. So that's an example of, you do weather. Climate is, you do the same, but you do it for much longer. And it took into account many more things. Actually, there are a few friends of mine here. So that's what people at NCAR, at the National Center for Atmospheric Research, are doing. I think it was done actually on a supercomputer at Argonne. And what you see, you have the time here, and you see the Arctic ice melting as the summer comes. I don't know which year it is, I didn't check that. But in their simulations, there seem to be all the north, the sea is free of ice. The Arctic Ocean, Arctic Sea. And now it's, the ice is coming back in the winter, and so on and so forth. I shall try not to bore you with taking each movie to its bitter end. So that's another example. That's also interesting. What you see, of course, is hot Pacific, and once in a while you see something moving very fast. That's a storm, which is cooling the ocean when it's happening. So once in a while you see this quick movement. It's tropical storms that moves. Because what you are shown here is the temperature of the ocean. So when a tropic storm moves, it cools the ocean. So that's another example, and it goes on, I don't know for how many years, but typically these simulations are done for 50 to 100 years to try to understand what's happening. Here is another one which is quite nice. It's a tsunami of Fukushima simulated, not, that's again a simulation. So you see it starting. And, and you see the time running. Well, 4 hours after it started, 6 hours. It gets to whatever, Guinea, 6 hours. Later it gets to San Diego, 9 hours after it started, and so on and so forth. And you see the reflections from, when it touches a shelf, and probably some islands which are causing all these refractions and reflections, which we don't even see. Here you can see, I don't know what it is. Is it New Zealand or? So you see all this. It looks like an experiment in your bathroom, but it is the Pacific Ocean and many hours. And it's a simulation again, which presumably people do to see that they can get it up. I moved one too fast. And the reason you do these simulations because you want to be able to predict the next one, or you want to understand if next one happen, what will be its impact. So that's the impact of a tsunami close to Seattle, and it tells you that there are some places where you don't want to own a house in Seattle because tsunamis can happen in Seattle. It's a distinct possibility, and you will see that some places get totally flooded by a tsunami. I don't know enough of, I suppose main downtown is here, if I remember, but I'm not sure. But you see some places get flooded. Here is the water getting inside. So, it's important to be able to know where you don't want to build or where you want to evacuate people quickly. You see, there is an area there that I would not want to be in if there is a tsunami. So that's another example of how you use simulation. And I don't have all the numbers. Some of the simulations I've shown are using more than 1 million cores. Some are using hundreds of thousands. So these are simulations that use really very heavy computing because they want to get things in astrophysics. That may also be interesting. You want to simulate, I think what they're simulating here, and NASA has nice video editor, so nice graphics. But what they're simulating is two black holes that are colliding with each other, and what happens when two black holes collide. And of course, it's somewhat hard to observe two black holes colliding in detail. So you do the simulation, and then you check against the information that you have from observations if it's consistent. So they explain what's happening. The two black holes get close. You get matter evacuated, and that's what they're interested to get right, because these are the jets that you can see at large distance of materials that gets ejected. And then you have one black hole, almost one. Now it's one. So that's another area. And I also picked a simulation from our friends at Beckman. That's Klaus Schulten piece of work. It's how the good cholesterol fights the bad fat. So what you have is a molecule of I forgot what, of good cholesterol, and they are essentially taking the fat and making it into spheres that then can move easily through the blood. And that's why you want good cholesterol, because it cleans up the fat. And you see the time frame here. We are discussing microseconds. And each of those is supposed to be a molecule. And you simulate its molecular dynamics. You simulate the molecule one by one. Sorry. By the way, if you want to ask questions, please feel free to interrupt. That's an example of use of computers in engineering. What did I do? You are simulating the flow of air around a car. Maybe people can recognize what car it is. Basically what it's showing, it's raising the plane, and each time it's showing how the air is moving that comes at a particular speed, at a particular height, how it's moving around the car. So you can see, you can get a notion of the airflow around the car, which is important because that determines the drag on the car, which impacts, its fuel consumption or speed, determines if the car is stable or unstable, if it's a race car, as this one probably is. So you use that in designing cars. I think I have, what did I do? I think I have one more animation. Oh, big thing. airports have increasingly noise abatement restrictions, so you want to make engines that don't make a lot of noise. So you simulate the noise, and that's what they're doing. That's probably a NASA simulation. Picking the music for somewhere. I doubt that So that's airflow coming out of the engine, and then they're going to, and now they are superimposing the noise flow, which you see, the noise, and you can get a notion of how far from the engine you will get a noise of what intensity, and people are working again and again on quiet engines, because then planes can fly into Midway or what have you, even at night, if they're quieter. So it's an important problem in engineering. And that's an example where you certainly don't want to design the engine, fly it, measure the noise, do it again, and do it again. So it's important. Oh, this one was done at Argonne on one. So these are examples of where we use simulation. How do you do it? Well, you start with some physical system for which you have a set of equations that describe the system, typically differential equations. Z, I'm told, is an equation that describes flow of liquids or flow of gases, a Navier-Stokes equation. I'm not a computation scientist, so don't ask me what these strange signs mean. But for a person that learned physics, that's meaningful. And that's the equation that tells you basically the intuition, at least for non-turbulent flow, is quite easy to understand. The speed will be proportional to the difference in pressure. But if air or flow is moving, that changes the pressure, and now so the pressure relates to the speed relates to the pressure, and you get differential equations that are relating these two. If you have turbulent flows, then you have to take into account also the drag, or essentially you represent turbulence as something that slows down the flow. So you have one of these equations. You need to discretize it. Computer cannot deal with continuous systems. It can deal with a finite set of variables. So the next step is to discretize it. You represent, say, the atmosphere by a set of cells. For each cell, you will have a variable or a set of variables, the pressure, the speed, depending on what you simulate. In climate, you may have temperature, you will have how much vapor you have, humidity, you will have chemical composition, and so on and so forth. So you get a set of variables for each point. You set your time step, and you are going to just the simplest method. That's not. There are other ways of doing things, but the simplest way of thinking is that you are going to iterate. You take the value at a point, at a particular time step. Each point impacts the values at neighbor points at the next time step. So you compute the new values, and you keep doing that time step after time step after time step. Provided, and the observation is that typically in physical system, a point is impacted with what happens in its neighborhood. So you don't have to have everything impacting everything, provided that the time step is small enough. Provided that the physics is so that what happens at a point can impact only the neighbor points, and the next time step cannot impact things far. So the size of the time step is going to be proportional to how fine the mesh is, or inversely, and to how fast things propagate through the system. Typically, for you simulate atmosphere, you care about speed of sound, which is as fast as things propagate in the atmosphere. If you look at simulating biomolecules, you care about the speed of light because you simulate fields, electrical or electromagnetic fields, which propagate at the speed of light. So the molecules, the molecular simulations that I've shown you are using time steps which are measured in femtoseconds to be able to get the right, this locality property. The climate simulations that I've shown you use time steps which are measured in half an hour or things of that ilk. And of course, the finer the mesh is, the more accurate your simulation is, because you are closer to the continuous case. But the finer it is, the more computations you will have, because you have more variables, and you have to go to smaller time steps when you go to a finer mesh. Now, meshes can be more complex. I think that's a Lamborghini for people that like cars. And you see, to get a good representation, they're using 358,000 triangles to mesh the... and of course, if you're interested on the flow of air around the car, then you don't have to mesh only the surface of the car, you have to mesh the air around the car. And I don't know how many... These are shown in 2D, so they are triangle, but if you think in 3D, they would be tetraheders that you are filling the space with. And if you look here, you see that close to the cars are using much finer tetraheders or triangles. And the reason that here the air flows much faster and is more turbulent, so you need smaller cells to be able to do the same. You want to use the same time step everywhere, then you have to have smaller cells where things are happening faster. For this principle that I said, that you don't want things to move more than one cell in one time step. So you get these strange-looking meshes, and now you do your simulation. Here is the type of meshes people are using now for atmospheric simulation. Older codes were using longitude-latitude, which has a problem that you have a singularity as a pole. Things get smaller and smaller. Newer codes are trying to cover the surface of the Earth with cells which look more or less the same. Can somebody see how this one was built?
Is it on the International Date Line?
No, well, possibly, but look at this here, what's happening. It's basically, you build a cube and you put rectangles on the cube faces, and then you blow it up to cover the sphere. So that's an example of how you build this kind of meshes. Here they're covering the sphere with hexagons, which gives something that's more regular. There are small ones, you probably cannot see it at distance. But the more complex the mesh is, the more complex is the code that deal with the interaction between elements in the mesh. So the basic law of supercomputing is that physicists always want more performance, and for two reasons. They want to go to finer meshes. So today, when you hear, the reports on climate, global warming, they come out of simulations that were done with meshes that were 100 kilometer or 1 degree wide, which is fairly coarse. Maybe in Illinois you don't lose a lot of detail, but if you're in California, you lose the Central Valley if you have 100 kilometer. So the next campaign will use meshes which are above 10, 12 kilometer, 1/10 of a degree. And remember what I said, you increase the resolution by a factor of 10, you increase the computation by a factor of 1,000, because you have 3 dimensions in space and 1 dimension in time. So very quickly, you can go to.
Do we expect that would change? Any conclusions on global warming?
I don't expect, you get more detailed I think there is a strong consensus that there is global warming. Whether Illinois will get drier or wetter, or how fast the ice is melting, or a lot of details which, there is a lot of uncertainty. You go to much finer simulations, you probably get these details more, in a more accurate fashion. And it's not only a finer mesh. What really takes a lot of time is that you want to go to introduce more and more what computation scientists call physics, take into account more and more phenomena. So if you care about global warming, you care about, in fact, I think I have a slice. That's the kind of things that you care in an atmospheric, in a climate simulation. You have to simulate the atmosphere and, of course, the solar energy and the clouds at different levels, and precipitation and evaporation. You care about snow cover, sea ice, the oceans, salinity, a lot of details, the land, the flow of water into the ocean and the evaporation back. So the cycle of water, you care about vegetation, because that impacts reflectivity of how much sun is reflected or absorbed. You care, of course, about the geography, mountains, and so on. So you try to take into account all of these phenomena. You get not a simple model, as I said, but very complex coupled models, which include a model of the atmosphere, a model of the ocean, a model of the ice, in fact, a model of the sea ice, a model of the land ice, vegetation, and so on, and so on, and so on. And you get more and more couplings, and at some point you have to introduce the peoples that may change what they are growing, or so you get more and more phenomena that you put into your simulations, and each time your code becomes more complex and more time consuming. So that's really where a lot of time is spent. That's, by the way, the current atmospheric code. It has atmosphere, and that's just CAM is a flow, the simple equations of flow. But now we have chemistry. I think that has to do with clouds, sea ice, land ice, ocean, land. And I don't have here, I didn't find it, there is a slide of what will be this code in 10 years, and the number of boxes is significantly larger. They keep improving, adding more and more components to this. And the other thing that takes a lot of time in simulations is that you want to do not one simulation, but many simulations, because there is always uncertainty. You don't know where you start exactly when you do climate, or weather. We don't have exact measurements of the state of the ocean and atmosphere and everything at any point. So there is some uncertainty. So you are doing many simulations, hundreds of simulations, which are starting from slightly different points, and see, if you are getting the same result, to what extent the result depends on where you start. Also, you need to do many simulations to try to validate your model. And one big issue when we do computational science is how the heck you know that your model really reflects reality. So, for example, climate, and that's why we have so many climate deniers, we have to wait 50 years to know if the predictions are right. So people try to go back. You simulate the last 50 years and you say if you get them right. But the point is, A, is that the last 50 years are probably different than the next 50 years because CO2 concentration increases tremendously. And B, the measurements 50 years back were probably even less accurate than they are now. So you have a lot of certainty of where you start your simulation if you started 50 years back.
So Mark, I have a question. When you're going back and you're looking at your model for to find out whether or not you think it's actually doing it, how much computer science knowledge does the person who understands the physics have to have?
Yeah, I shall get to it in a moment.
Okay.
All this, not in a moment, maybe never, at the speed at which I go. But the point is that these codes are typically developed by large teams which include people that are more on the science side, people that are more on the algorithms, computation methods, people that are more on computer science, how you use efficiently a large machine. So typically we'll have a team of 10, 15 people with varied skills, and once the code is reasonably stable, as is the case for these climate codes, then they are going to be used by hundreds or thousands of users, which are just turning the crank, using them essentially as a black box, trying them with different inputs or different initial conditions or different combinations of these various modules and so on and so forth. So in the development, it's going to be a joint effort of people that cover everything. Once they're reasonably stable, they are yet one more tool used by computational, by people that do atmospheric science or research in biology or what have you.
So as soon as Blue Waters goes online, there's already a queue of people
Yeah.
ready to make use of it. And is it 24 hours a day?
Yes.
This thing is.
Yeah, I shall get to it in a minute, I think. Anyhow, you probably have seen many times these kind of diagrams, and that's come from running multiple simulations. And in one of them it goes this way, another goes this way, and you try to get some average or something. Okay, that's a parallel computer. Or that's a parallel computer as designed probably more than 100 years ago. I don't know if people are aware of the, you see here people, can you see them? These are computers. The word computer before 45, was used for this kind of people that had a paper and pencil and were doing computations. So what you have here is a big simulation of the atmosphere, probably weather prediction. You have computers spread around, all around the surface of the Earth. Each one is doing the computation for its piece of land, and it's exchanging information with its neighbors. Maybe, I don't know, maybe it was a centralized approach where you send your results to the control room, to the center of the Earth, and it's sent back. So that's how you do parallel computation. You have a lot of computers, each one pick a piece of your systems that you try to simulate, and they do their computation and exchange information with their neighbors.
Is this drawing 100 years old, or is this?
It's old. It's old. I don't have the source. I didn't have time to look at it, but it is the conception that some mathematician had about how you can simulate the weather. And I don't remember how old it is.
In this weather model, is that a deterministic model, or is there stochastic things in it? You have to run it again.
The models that people are using are deterministic, but they do uncertainty quantification by running it with, with slightly different initial conditions.
But once the conditions are set,
It's deterministic. It's the mathematical model, yeah. Okay, so that's a parallel computer. And, Blue Waters is the same idea. You just replace the human computers by digital computers, and they're doing their computation and exchanging information with their neighbors. That, I think, is Blue Waters. And it's the same logic. Sometimes you need to communicate with the center of control, the center of the Earth. Sometimes the communication is more complex than just communicating with your neighbors, but it's a bunch of computers connected together that can compute. That's Blue Waters, by the way. Just for people that are interested in these things, that's not Blue Waters. That's actually a tape silo. So if you're standing here, what you are seeing is 2 rows full of tape cartridges and the robots that can move them and mount them and dismount them. So all these 4 rows are really robots of tape cartridges. Blue Waters is there in the back. So it's very nice if you have not visited. And really, these robots are the more interesting part of the installation. That's Blue Waters. It has basically something like 25,000 computers hooked together. Each computer has 16 cores. So each computer, each node here, what's called a node, is basically a high-end workstation. Slightly more powerful than your laptop, less powerful than whatever workstation some of you may be using. And you have 25,000 of those, which comes down to 38,000 cores that are hooked together and compute. I won't go into the details. Basically, all these nodes are connected together in a 3D mesh, 3D torus. You can think as a surface of the big machine room, and then the height of each rack, and then you have the disks which are somewhere. You have connections to the network, connections to the outside world, and so on and so forth. So that's basically a supercomputer.
Wait, was that how they're physically arranged? Or?
Yeah.
Mm-hmm.
Yeah.
Okay.
Yeah. Yeah. The physical. The idea is that you want to have short cables. So 3D toruses are very easy to arrange in space. Now, unfortunately, vendors go to 5D toruses, so multi-stage networks. So now it becomes harder to arrange it correctly in space. But 3D, yeah, we know how to manage 3D. I think it has something like 20,000 or 30,000 disks, which means that one disk is always, disks are failing daily or whatever, or weekly. So huge amount of I/O, and the tape is supposed to grow to, the disks are 26 petabyte of storage. So if we assume they are using 1 gigabyte disk, that will be 26,000. And you need more for redundancy. So I think it's about 30,000 disks. And then the tapes, which can get 10 times as much storage. So you asked me if it's running. Let's see if it's running. I hope I am connected to the internet. Maybe not. It's supposed to be. I don't have my internet connection. But if you go to the Blue Water site, there is a web page where you can see what is running at this point in time on the machine. And maybe I can try to do it because it's amusing. How do I get out of this? So it's, well, it's probably, can go to NCSA. Illinois.edu. No. Okay, so I'm not connected. So I shall continue with my talk. But if you go...
I think your URL might have been off there. It was, you had www.s.
Oh, okay. It might work if I correct it. Thank you. And somewhere...
Secret network we didn't
Yeah.
Make a note of that.
So somewhere, where do you get it? Oh, here it is. Running your job, storage. Where is it? I'm going too fast. System status, probably. No. Oh, jobs, probably. Nope. Okay, we'll give up. But there is a page where you can see what's running at any point in time. So 78% is used. 25% at this point in time is idle, and somewhere you can see the projects which are running at any point in time. So you can have, and last time I checked, it was running 6 or 8 major projects in astrophysics, biology, what have you. So somewhere you can go, we can do it later, rather than me trying to recover this. Maybe it will work. Oh. Yeah. No, it has. Oh, here it is. So you see what's running at this point in time. Can I move it a little bit more? So that's what is running. And you can see, if you click, lattice QCD is theoretical physics, astrophysics, heliophysics, supernovas, again physicists, computational chemistry, whatever, computer science. So you can see at any point in time what's happening on blue waters. Okay, sorry for this long interruption. Why are supercomputers expensive? A lot of hardware. The hardware of blue waters is $200 million, plus minus. Expensive machine room. The machine room here is $60 million, plus minus. A lot of power, electricity. The blue water, the building, I don't say the machine consumption, the building is designed to be able to use 24 megawatt. That's a lot of power. In fact, it's built to have 32 megawatt coming on 4 lines of 8 megawatt. So if one line is down, the other 3 are sufficient to feed.
Do you need its own power supply? Do you need your own cold?
No, actually, there is one line from the local power plant and 3 lines coming from whoever is our supplier, but 4 different high voltage lines coming onto this building. So just to give you a feeling, the machine is water cooled, so a lot of water pipes going to the machine, and I don't know if people have noticed, but up there are cooling towers in order to be able to recycle the water, and many of you have certainly seen the big water tank which is close to Nil, which is the water tank to cool this machine.
Where is this machine now exactly?
It's, where is it?
Side of the railroad track.
Yeah, close to the railroad tracks, St. Mary or what's... So it's a big building. If you go there, you will see it. But it gives you, it's a plant. Here are the power supplies, again, the floor below the computer. This thing is amusing. There is, computers are on a raised floor because you want to be able to bring cables, power, and so on. That's a raised floor. It's 6 feet raised. And the reason you need it is because you have the big water pipes and because you have a lot of cables running from anywhere to anywhere. So it's interesting. If you go there, you should bribe somebody to allow you to see all the plumbing for sure and the raised floor.
So Kathleen and I went over for an open house there, and one of the things that was most amazing is the noise. You would think it would be quiet like
Oh,
the
no.
library, but it is, everything that's moving around in there is so noisy.
Actually, almost all the noise comes from the spinning disks. And that's moving. Why is supercomputing hard? Well, think of an orchestra with 400,000 players. That's a supercomputer. And it's somewhat hard to coordinate all of them. And one of them breaks down all the time. So How do you cope with that? How do we program them? We write programs, basically one program is running on each of these cores, or each thread, and then we're exchanging messages between them. So I can send a message to node 1, can send a message to node 36,000. The node 36,000 can receive a message. That's point-to-point communication. You can access memory on a remote node. You can write memory on a remote node. That's what we call put and gets. But you don't have shared memory across all these nodes. No way. Or you can have a barrier. Everybody waits until everybody has gotten to the barrier, or an operation, collective operation to reduce. Each one has a number. You want to compute the sum of all these numbers to know, for example, if you can stop your computation because your error, cumulative error, is small enough, things of that kind. So that's basically how we program. Nothing very highfalutin, sequential program plus messages. How we debug? Barely. How do you see what 400,000 threads are doing? You cannot have one window for each of these threads, so it's a major problem, actually, how to debug parallel programs. Luckily, most of the bugs are found when you run on a small scale. And then the remaining bug or two that really drive you nuts is, what happens only at big scale.
So that goes back to my original question, because when it comes to the debugging, is it always the computer scientist that debugs, or is it the scientist?
It's the computer scientist or the people that wrote the code.
And they have to communicate?
Yeah.
Okay.
How we tune, clearly for machines that are so expensive, you want to tune them carefully to get performance. And that's a hard problem as well. It's how to get good performance on one node. In fact, it's a skill that most computer scientists have forgotten. We write programs in Java or what have you, and is it efficient or not? Who cares? But when you write supercomputing programs, you care about efficiency. And after you get your code running well on a node, do you have enough you may have too much communication. Or even if you don't have too much communication, it could be that some nodes have more work, some nodes have less work. So the work is not balanced. Or maybe all have the same amount of work, but it's not balanced correctly. So one is going ahead and now has to wait for another one. The other one catches up. The first one now has to wait. And, depending on how things are coordinated, you may have a lot of idle time because one node is waiting for another node to have progressed on its computation. How do we write to disk? The simpler answer would be to have a disk for each of the nodes, but then at the end of your simulation, you would have 400,000 files to look at the result, which is problematic. So typically, you have parallel file systems where files can be spread across many disks, so many processors can simultaneously write to one file, which is spread across many disks. The problem, as I said, is that disks always fail. So what you do, you use RAID technique, which means that you don't keep only your data, but you always have parity somewhere. So if this disk has failed, I can reconstruct all the data that was here from the blocks that are stored on the other disks, because always these four blocks, sum together to 0, 0, 0, 0, 0. So any three of these blocks is sufficient to reconstruct the fourth one. So that's what we call RAID in computer science. That's how you can maintain files even so, disk crash. And in fact, I think we're using not one, but two, so that we can tolerate two disk crashes before the system has to stop. So that might be my last, no. How we cope with failures. Very simple, checkpoint and restart. Periodically, every 4 hours, you dump your computation on disks. If the system crashes, you go back to your last dump and start again from this dump. That's basically what we do. Very simple-minded. That's supercomputing in a nutshell. If there are any questions, please feel free to ask.
How old is the facility that's at Argonne?
Argonne has been in the supercomputing business forever, since ever. Argonne was opened in '46, I think, and the big first supercomputer there, which probably is much smaller than your or much weaker than your current cell phone, it was installed in '50 something. Our current machine room, I think, is 3 years old, something like that. So quite new as well. But we don't have 6 feet tall, raised floors. And I asked, why don't you do that? You don't have to crawl. Well, it turns out that in DOE, if the crawl space is more than 4 feet, you need additional safety arrangements. So they always build them 4 feet to be below the point where you have safety complications. Things are always strange. I had somewhere the bandwidth, so I think it was in one of my slides from which you can see. Actually, yeah, where was it? Blue Waters. Yeah, no, that's quite fast. Most of the time, the time it takes for a robot to move maybe a few seconds. It's much shorter than the time it takes to actually read the tape. Where was it? I had somewhere. Oh, I forgot it. I think I had a. Again.
If you go to Blue Waters, you can actually see the robots moving.
Yeah.
There's between the stacks, there's a window, and you can watch the robot, and it comes and takes that.
Yeah, it takes, to load one of these cassettes take only a few seconds. To read it entirely may take tens of seconds. I don't know exactly. You can see, I think each one is about, you can look at the speed of this, the reading speed and the amount of data that is on each robot, and you divide, I don't remember the number, but it's tens of seconds.
When will Blue Waters become obsolete?
Oh, yesterday? No, it's typically use these machines for 4 or 5 years. So if you think that it costs $200 million, the depreciation is 50 million a year or something. And after 5 years, you just junk them.
So the black hole collision that you showed us, do you know anything about that at all, that research? Like, my question is, are they reconciling their simulation with data that they collected before they even knew black holes existed?
They reconcile the simulation. Basically, when two black holes merge, at some point there is this jet of material that's ejected, and I assume it goes also with electromagnetic radiation. So you try to see that, this ejector, matches whatever observation we had that we suspect are black hole collisions.
Yeah, so some of these observations could be decades old, and they knew what they were seeing, but they didn't have any way of deciding what they thought they were seeing?
Yeah, but the point is that if you go too much back in time, you don't have any detail of how long it took, what was, was it white or red or whatever, so it's very hard to do that. But the point still is that your observation is a very small window on what's happening there. You match it, okay, so that gives you a good feeling, but maybe there are different models that could match the same observation, and that's harder. So there is always some residual uncertainty for phenomena that are hard to really explore.
Is Moore's law continuing, or is it running up against the wall?
It's running up against the wall quite quickly, probably in 10 years or so.
So I can't get a Blue Waters on my desk in about 10 years.
No, and what we do after that is a very interesting question. I hope to be retired, so but it's a very much nagging question. It could be basically for 20 years we had a nice run because we have been using technology from the mass market. workstations and so on. In 10 years, if the mass market stops moving as fast because we get at the end of Moore's law, then either supercomputing stops advancing or it has to use exotic technologies that are much more expensive. And nobody wants to face this dilemma before the sky falls because, it's a hard choice.
Do these exotic technologies exist?
Yeah. There are, you can use, many companies have done for years research on superconducting transistor or transistor using superconducting technology. And these are machines you can run at 50 or 100 gigahertz rather than the 2 gigahertz. So that would give you, at least 1 or 2 orders of magnitude improvement. Also, you can you can have much denser circuits because they are super cooled, so and they don't consume that much energy. So you can build systems that are much more compact. So yes, this technology could be used, but it's used now in very few devices at very small scale. And a 3-letter agency is investing in this technology, but most of the world is still reluctant to consider it.
I'm talking about something I don't know anything about, so I may not be able to formulate the question very well. But it's my understanding that there were problems in number theory that people thought were too complex and would require too much computation. And then it was discovered that by parceling these things out to 500,000 PCs, they were able to get answers much faster than they thought they could.
Yeah.
What is the competition between the super?
Well, the problem is it a problem that can be executed by, or in both cases you need a lot of tasks which execute in parallel. The problem is how much they need to communicate. When you do a simulation of the types that I show, you have to communicate at each time step. There is a lot of communication. If you are trying primality test, and you just try, many independent tests until you find the answer, then you can send it out to people to do that on their own workstation, collect the results, and then see what happens. So it's really how decomposable the problem is, or how much communication, coordination you need between the parallel components.
Will solid-state drives be used in supercomputers at some point? Will solid-state drives be used
for sure.
Are they currently, or?
No, there are already supercomputers that use solid-state drives, but the expectation is less solid-state drive, but once it appears in the form of non-volatile memory, that probably 5 years down the road or something like that. One reason is that I described checkpoint restart. It takes 15 minutes to checkpoint a big application when you do it on disk. If machines start failing more frequently, then you are in trouble. If you do it in NVRAM, you probably can do it in seconds. So I can tolerate something going wrong even once every half an hour or something, and still be alive. Okay.
This was fantastic.